So we want to do a little bit of calculus with parametric curves. And the first thing we're going to do is figure out how to take the derivative. Specifically, how do we take the derivative of y with respect to x when we don't have y with respect to x, and maybe we can't solve for it, but we have x and y in terms of t. So for example, this graph that I've put on the board behind, these are the this is the parametric equation for that graph. This is your x and your y, and I put this into Desmos to make the picture. Well, I just drew it on the board here, but you're welcome to go and put it into Desmos to make a better picture. What you can see about this graph, though, is it curves and twists, kind of like a nice little river, but you can kind of see that it's got some horizontal tangents, right? Like somewhere around here it looks like it's the top of a hump, and somewhere down here it looks like it's the bottom of a hump. But it also has vertical tangents, because here, somewhere around here, it looks like it's going straight, and then somewhere maybe around here, it looks like it's going straight. So these are the kind of things that we might want to figure out. We might want to figure out what the tangent is at some arbitrary point, or we might want to figure out where the top and the bottom of the graph is. Before the advent of the graphing calculator and you could just put it in, this was an important way of figuring out how to draw the graph, is to find where the horizontal and vertical tangents were. Now it's sort of important for other reasons, right? But in any case, that's what we're going to try to do. In order to do that, we have to know how to take the derivative. Okay? So when I'm talking about finding the horizontal and vertical tangents, again, I'm talking about finding the dy dx. Okay? So I need to have a formula for dy dx in terms of what I can figure out. I can figure out dy dt and dx dt. So let me just use the chain rule really quickly to show you where this comes from. But you don't have to remember the proof or anything. You just have to remember what you need to do in the end. So if I really want to think about dy dx, I need to think about y as being a function of x. So that would be, let's imagine eliminating the parameter like we did in the previous examples. Well, of course, we don't want to eliminate this parameter, God forbid. But let's pretend we did it. Let's pretend we wrote y as a function of x. And now I'm going to use big F of x. So I forgot something. So I'm starting out with parametric equations, x and y, both as functions of t. Pretend I was able to eliminate the t and wrote y as a function big F of x. Then dy dx is actually f prime of x. So that's what we're looking for. Okay, but we don't know big F. What we know is little f. So what I can do is take this equation. If I write that in terms of t, I get y equals big F of x, little f, or even better, g of t is f of ft. Now chain rule, I just take derivatives of both sides. Okay, but little f of t is just x, so I can rewrite this as f prime of x, little f prime of t. Well, that's what I want, f prime of x. So if I can solve for that, that actually tells me how to find the slope or the derivative. Personally, I find it, so you can remember it in this form, okay? You can also use the Leibniz notation. I prefer it on myself because for this, it's much easier for me to remember. And in Leibniz notation, this is dy dx is dy dt divided by dx dt. And that's Also easier to remember because you can kind of think about the t's cancel out, which doesn't really, but you know, it's the idea. So whether you remember it in this form or in that form, it means it's actually pretty easy to find dy dx. We just take the derivative of y and divide by the derivative of x. All right, I'm going to write that up here. And that is all fine and dandy unless I'm dividing by 0, so we can't be dividing by 0, all right? Okay. So here's a little thing. Now if I want to take this curve and find all the horizontal tangents, that would be these two. Well, let's find out what dy dx is and set it equal to 0. Right? So dy, this is the y. Then dx dt is in the bottom. Okay. Fine. So a horizontal tangent is going to be where dy dx is equal to 0, which is then going to just be where that top is equal to 0, right? So 6t squared plus 6t equals 0, and the bottom is not equal to 0. So dx dt is not equal to 0. I have to point that out. But in fact, of course, if this is equal to 0, then that's going to be negative 12. So we're fine. Okay? So let's solve for those possible t's. So I'll take out the 6t here, and then I got t plus 1. So that looks like t equals 0, and t equals negative 1. So that's fine. Really what we want, though, they'll always be asking you for the coordinates of the points, meaning they want the xy coordinate of the point. So even though we found the value of the parameter that gives us these 2 points, we also have to find the xy coordinates. So we have to plug these numbers back into our original form so that we can find the points on the xy graph. Okay, I want to keep that. So let's do that here. At t equals 0, x equals 0, y equals 1. So that is this point right here. At t equals negative 1, x equals minus 2 plus 3, plus 12. So that looks like 13. And y equals minus 2 plus 3 plus 1, so that is 2. Okay, it doesn't really look that great on my graph, but if you do it on Decimus, you'll see that is this point here, x equals 13, y equals 2. Those are our 2 horizontal tangents. Okay, now, the other question is vertical tangents, right? Because these guys are vertical tangents. So a vertical tangent is going to happen when this dy dx goes off to infinity, plus or minus infinity, right? So, like our horizontal tangents are going to be where this is 0 and that's not 0. Vertical tangent is going to be the other way around. So, vertical tangent is going to be where that bottom is 0 and your top is non-zero. Right now, why does the top have to be non-zero? Because if bottom and top are 0, then I have 0 over 0. 0 over 0 is an indeterminate form. It's not going to happen for this curve, which is why this is a good curve to use as the first example. We'll do another example where there are some of those, you have to deal with them. That's a real pain because when it's an indeterminate form, you have to take the limit, use L'Hopital's rule, blah, 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 right? So, but we don't have to do that here because when this guy's 0, that guy's non-zero. So I have a number divided by something that's going to 0. That's going to give me a slope that's going to infinity, which is exactly what we want. That's exactly what our vertical tangent is. It's where the slope goes to infinity. Okay? So going back to this is easy enough to solve for, right? I just pull out my 6. I have a nice plus 2 t minus 1, nice quadratic. So now I have t equals 1 and t equals -2. So, which is nice because I know I'm looking for 2 points from the graph. I'm going to figure out what those are. So let's plug those in. Okay, at t equals 1, x is 2 plus 3 minus 12. Okay, so okay, so not quite -10, right? -9. No, wait. Yeah, 5. God, I can't add. Thanks. No, it's not right. But, yeah, it is. It's right because it's 1. Positive 1, so positive, negative, not -7. That's fine. Y is 2 plus 3 plus 1. All right, is it 6, not 7? Is that why I'm confusing myself? 5. No, it's 7. 7, 6, whatever. Okay, fine. In any case, it's here. Those are the coordinates at this point. I just can't add, but that's not news to anybody who's been in this class. So here for t equals -2, I'm going to do the same thing. I'm going to plug them in there to find the coordinates of my point in my xy plane. 2 times 8, and then 12 plus 24. What the heck? What is this? 36 minus 16 to 20. Oh, that looks right. That looks right. Y equals minus 16 plus 12 plus 1, so minus 3. Okay, well, it's a little bit down too far on my graph, but more or less, I'm agreeing with this. That looks about right. Those are the coordinates at that point. So I found my coordinates of both of my horizontal tangents and my vertical tangents.